Hi everyone. So in this video, we'll talk about exponential growth and decay functions and their key features. Okay. So exponential function is the function that is in this form. Like we do have like f of x b to the x, which means the variable is the exponent. But you could just say, let's say y equals like b to the x. This is just the most basic ways to say it. But we could have, let's say, y equals 2 times like 3 to the x, which means in front of the b, you could have some numbers as well. So this is going to be still exponential function. So let's say 3 times 1/2 to the x power. So this is also exponential function. So I guess we can make this a bit general. So the y equals a times b to the x. So whenever you have a function can be written in this form, we call that exponential function. Okay, b is a positive number. So 1/2 is a positive, 3 is a positive, and other than 1, because if you choose b as 1, so we have 1 to the x power, regardless what you plug for x, you will always get 1, so which means it's going to be a straight line. So that's why we don't accept 1 for b. And exponent x is a variable, which is the unknown. And the function represents exponential growth if b is larger than 1. So I'm going to ask you to think about this y. Okay, so if your b is 3, so this function will be called exponential growth. If b is like 1/2, 1/3 and stuff, that will be called exponential decay. If this is smaller than 1, but larger than 0. So we don't accept any negatives for this exponential function, okay? So that's the definition. So based on this, let's look at what we have. So we wanna graph the 2 to the x and 1/2 to the x, and to see their relation. We have some of the points already given for us. So let's think about the remaining points, okay? So at this point, I'll allow you to pause and complete the rest on your own before you see the mine. Okay, but I assume you just did now. So 2 to the x, if you plug -3, so you will get 2 to the -3rd power, which is 1/8. If you plug this, you will get 2 to the -2nd, which is 1/4, and this is 1/2. If you choose 0, 2 to the 0th power is 1. If you choose 1, 2 to the first power is 2. If you choose 2, so you will get 4, and this is going to be 8, okay? And if you plug -3 for x, so you will get 1/2 to the -3rd power. When you have negative power of a fraction, you can just flip these upside down. So you will get 2/1 to the 3rd power, so which is 2 to the 3rd. That's why we got 8. And if you have -2, so you will get 1/2 to the -2nd power, which will be 2 to the 2nd power, so which is 4. And this is going to be 2 if you do the same logic. If you try 2, so 1/2 to the 2nd power, so you will get 1/4. And for 3, you will get 1/8. Okay, so we complete the table. So we are good with that. And which function's value increase? Actually, I should have said this first, but that's fine. So as you see, this function's value is like 1/8, 1/4, 1/2, 1, 2, 4, 8. This is increasing. And then these numbers are decreasing as you increase the x values. Okay, when you improve like inputs, like which is x in this case, increases, the y values right here is increasing, but y values right here decreasing. But as you see, none of them is negative. Like regardless of what you plug for the x, so positive or negative, the result is always positive. So if the base, which is 1/2 and 2, is positive, so you expect to get always a positive result. Okay, so we are done with that. The graph of the f of x and g of x are given below, which is I'm going to show you in a second. And then use the graph to identify the following key characteristic of this function. So maybe we could actually draw them based on these points. So let me do that in this figure. Okay, so I think, yeah, this is good. So yeah, let's try now this one, right? So I'm gonna clean this mess. But I want you to remember these points that we had, so because that's what we need. So we do, like, this was 2 to the x power, so this was 1, this was 2, 4, 8, and then this was 4 to 1 over 4 and 1 over 8, if you remember. So this is f of x, so maybe we can use this graph. So when you plug 0, you will get y is 1. So this is 1 point. And then 1 comma 2, so 1 comma 2 is right there. 2 comma 4 is right there. 3, 8 is right there. If you plug -1, that's going to be 1/2, so it will be something right there. If you plug -2, you get 1/4. So it's going to be getting really closer to 0 now. If you choose -3, it's going to be 1 over 8, so something like that. So if you were to connect these points with your best ability to make nice curve, so you will get this guy. Okay, so this is f of x, which is 2 to the x power. And for the second one, I will use the same thing. -3 is going to be 8, so you had -3 is right here. -2 is 4, so actually no, that wasn't -3. So -3 is right there. And -2 will be 4. -1 is 2. And 0 is 1. 1 is 1/2. 2 is 1/4. It will be getting closer to. So if you look at the now these points to make a nice kind of curve. Since I'm using the tool, that doesn't really make me a nice curve, but it's okay. So now we have this one as g of x. Okay, so this was equal to 1/2 to the x power. So, okay, so now let's look at this part C. So the domain and range, like if you look at this function, f of x, you could go all the way to the left side, and then you can go all the way to the right side, which means there is no restriction for the x-axis. So domain is all real numbers. All real numbers are good for this function. And this is also the case. So you can choose any x value. So that's also the same for both. And the range, you're like getting closer to 0 as y value, but you are not really achieving that. So you are going to get closer to 0, but anything higher than 0 is possible. And the same thing with this guy as well. So the range would be for both function is anything larger than 0 all the way to the positive infinity. We can use this notation. Okay, and that's the domain and range. The end behavior, so when you like remember the end behavior, just like what do you get like when you make x as large possible. So if you move x to the right, so your function is getting bigger and bigger, so your like end behavior is positive infinity for this function. But for this function, when you choose if you choose x getting closer to positive infinity, your function is getting closer to y equals 0. So your end behavior is getting closer to 0 if you go to the right. If you do the other way around, so you're getting y values as possible. So like depends on what direction you are looking. So we could say two different things for the end behavior. So let me do this right here. So the end behavior of this g of x function is as x approaching to positive infinity, okay, then the y value, okay, when you approach to positive infinity in the x direction, y value is getting closer to 0. So that is your end behavior. And if x is approaching to negative infinity, the y value, like if you just go from left to right, right to left, your y values are getting bigger and bigger all the way to positive infinity. So that's going to be your end behavior. And if you were to do the same thing with the f, so if x is approaching to, so let me do the color coding. So if you approach the, in this case, to positive infinity in the x direction, if you just go this direction, your y is getting bigger and bigger. So if you're approaching to positive infinity, so your y is also approaching positive infinity. Okay, so, and if you approach to the negative infinity, okay, so if you go from right to left. So your y value is getting closer to 0, y equals 0, right? So that's your end behavior. So horizontal asymptote, so maybe I can do this way, which is kind of obvious at this point. So horizontal asymptote is basically the line that you are approaching on the horizontal axis, which is, this line is the horizontal asymptote you're approaching, because you're not really touching to this line, which is the x-axis, but we have a name for x-axis, which is y equals 0. So the horizontal asymptote is right here. Horizontal asymptote is y equals 0. And it's the same thing for both. So this graph is also approaching to the y equals 0, right? So that's your horizontal asymptote. And the y-intercept is actually the same for both. So 0, 1. This is also 0, 1. So we are done with choice C. For the part D, describe the similarities and differences of these two graphs. So the first one, the 2 to the x like function, your function is getting bigger and bigger as you go from left to right, which means if you increase the x values, your function is getting bigger and bigger. And then we have a name for this one, which is exponential growth, okay? And this guy is getting smaller and smaller when you choose x's larger values. 1 over 2 to the x power is exponential decay, basically. So we can kind of say that. You can add more comments, but I think this is fine for now. And using the key characteristic from part C, what generalization can you make about these two functions? Okay, if b is a positive number other than 1. So like, if you remember this one, this was 2 for b, right? So which is a larger than 1. If that is larger than 1, your function is getting bigger and bigger, which is exponential growth. So like if I have 1.1 instead, that will be still the case, because if you multiply 1.1 by like any power, like when you increase the power 1.1 to the second power, to the third power, to the fourth power, so you will always getting bigger than what you had in the previous one. So because your number is larger than 1, when you multiply something by larger than 1, you are getting bigger. So if you don't kind of see it, you can go ahead and actually plug that 1.1 to the second power, 1.1 to the third power, and continue a few more to see the change. And so that's why if the base right here, b, in just expansion, like expression, is larger than 1, we can say the function is always increasing, okay? So that's exponential growth. But if the b is lesser than 1, but larger than 0, which is like 1/2, 1/3, 1/5, and stuff, that is the exponential decay, which is your values are decreasing as you go. So we can make that general statement. And I'm going to leave the last part as a challenge for you. Let me show that first. So the last two is right here. So let me clear this piece. So for the f of x2 equals 2x, g of x, x squared, and h of x is 2 to the x power. So these are three different functions. This is a linear function because x has power 1, and this is square, like root, like square, which is quadratics. I can say if you graph it, you get a parabola. So that's another function type that we've seen, and this is now exponential. So make a table of values for x from 0 to 5 for each of those three functions, and graph three functions on the same corner plane, and describe what you observe as the values of x increase, and see which one is actually increasing way higher than the others, and compare them. And then I will leave for you to make a comment. So I will just leave it as a chance for you, okay? For F. And for G, find and compare the rate of change for f of x and average rate of change for g of x and h of x for each of those two consecutive values of x in the table that you have actually from part F. So again, these two are connected, so you have to finish this first, and then based on those values, you will continue this one. Basically, it's right here asking when you have the like 5 different like the points for each graph, then you're gonna find the rate of change for each function and compare them. Okay, so and then I will ask you to complete those two to see what you observe. Okay, if you do get that, so that will be really nice to see exploration. Okay, so I'll see you in the next video.